Hello everyone, welcome to the presentation, City-Level Digital Twin for Strategic Planning, Learnings from Cambridge. This paper was submitted to the Data for Policy 2021 conference, session number 45, towards smart city planning, digital twins and the parallel world scenarios to support better public policies. Please allow me to introduce myself and my co-author. I'm Dr. Li Wan. I'm the lecturer in urban development and planning at Department of Land Economy in Cambridge. My co-author, Dr. Timea Nochta, she's a senior research associate at the Cambridge Centre for Smart Infrastructure and Construction, hosted at the Department of Engineering in Cambridge. The presentation today has two sections. First, we're going to discuss three emerging challenges around the city-level digital twin development and propose our own propositions as a response to those challenges. Some of the propositions are originally proposed in one of our conference papers in 2019, but today's presentation includes some new extensions. In the next section, we're going to share some lessons from developing a transport digital twin prototype for Cambridge. This is a project funded by the Centre for Digital Build Britain and the Cambridge Centre for Smart Infrastructure and Construction in collaboration with the local authorities. Let's start from the new challenges and propositions. Challenge number one relates to the origin of city-level digital twins. As you all know, that the digital twin concept is not new at all. In the manufacturing sector, there has been numerous and also very successful digital twin examples, notably the digital twins of the turbo engines for the aeroplane. But the city-level digital twin concept is relatively nascent and only appeared in the last couple of years. In terms of the transition from manufacturing digital twins to city-level digital twins, does it represent a simple change of scale? To probe into this question, it might be useful to examine some distinct features of a city-level digital twin. First, the city-level digital twin has to address the nexus of a large number of subsystems or sectors in the city. For example, transport, housing, energy, and public services, where the interactions are beyond physics. By no means this is to say that those interactions cannot be quantified, just like what we do with the universal law of physics. Rather, it points to the fact that those interactions might be quite difficult to measure, and sometimes it's controversial to measure. The second point relates to the number of stakeholders involved. The more stakeholders involved in the system, more likely will observe conflicting interest. Those conflicting interests and the underlying considerations are often very hard to measure for modelers. So this raises a technical challenge for modelers in terms of represent those conflicting interests in the model. The last point relates to the purpose of the city-level digital twin. One of the common goals of the manufacturing digital twins is to optimize the manufacturing product or the process. Given the boundary condition and also the objective function, it is possible to derive an optimum solution in engineering terms. However, for city-level digital twins, the concept of optimization might be quite difficult to grasp. And again, it could be controversial in a socio-political context. A realistic goal of using the city-level digital twin is perhaps to support participatory and deliberative policymaking. It means that the city-level digital twin does not necessarily have to provide an optimum solution, but rather to support effective policy debate. So here is our first proposition. City-level digital twins cannot be interpreted as a product or generic technology, but rather as a new approach and a methodology for leveraging the value of data and digital technology in supporting participatory decision or policymaking. To understand the CDTs as a new approach and the methodology, there are some key dimensions that we can consider. So in the diagram on the right-hand side, you see a big box in the center. So this big box is a federation of digital twins. Each of these small boxes is a small digital twin, serves a certain purpose. The first dimension is the policy domain and the range of stakeholders involved. This relates to what the digital twin is for and for whom. The second dimension is the spatial temporal scale and the resolution. This may sound like a technical consideration, but actually the spatial temporal scale and the resolution reflects the purpose that the digital twin serves. And the last dimension is the socio-political context. This refers back to our proposition that CDT is not a generic technology that could be deployed without considering the specific context of the city. We should note that these three dimensions are not exhaustive, but considering these dimensions will help us to understand the nature and also the categorization of digital twins. Challenge number 2, how real-time is real-time. Real-time has been celebrated as a key feature of digital twins. But for cities, the term of real-time is somehow very ambiguous. So here we provide two examples that we can observe in the city. On the left-hand side, this is the population change in London. The grey line is the population in Greater London as a whole, and the blue line and orange line is the population in Inner London and Outer London, respectively. If we look at the rate of change, from 1900 to 2011, the average annual change of population in London is about 1%. And if we infer the daily change, the percentage change is actually 0.003%. This is a very, very marginal figure, which suggests that for population projection purposes, considering the daily change of population in London perhaps is not too useful. By contrast, on the right-hand side, this diagram shows the number of commuting cars in Cambridge as a function of how long you park your car at the workplace. For example, we observe that there are 400 commuting cars in Cambridge, which would park at the workplace for about 7 hours. But this number would increase to about 1,200 for those who parked at the workplace between 8 to 9 hours. Again, if we look at the rate of change, the hourly rate of change could be up to 50%. So the implication is that for a digital twin that aims to manage the traffic volume around those workplaces, it is critical to consider the time of the day and the day of the week differences. By showing these two distinct temporal scales in the city, here is our proposition. Real-time is a relative term. The spatial temporal scale of the city-level digital twin should reflect the rate of change of the subject system or process in reality. Higher spatial temporal resolution does not necessarily indicate better models. In other words, a single pursuit for high spatial temporal resolution of the model does not necessarily lead to better outcome of the model. For city-level digital twins, the real-time being a relative term poses a great analytical challenge for modelers. The table on the right-hand side shows the varying time scales of urban change processes, ranging from the very fast changes, for example, which travel mode you're going to use to go to work, to very slow changes, this is the construction and the maintenance of major infrastructure. It's unlikely that a single city-level digital twin could address all these timescales. Challenge number 3. Digital twins are useless if they can't predict. But what's the point of making predictions if they cannot drive positive changes? So this challenge is inspired by a recent paper on digital twin development published on the Nature Computational Science. In this paper, the authors argue that being able to predict is a fundamental use of digital twins. However, in the engineering sector, it somehow assumes that the good predictions will lead to good outcome. But this is not necessarily the case in the policy world, in cities. For a city-level digital twin model for drive positive changes, The twin model has to go through this long process of translating data into policy insights, and then striving for consensus among stakeholders, and then to policy actions. So in the end, it's not the machine, it's not the twin model that will generate the change, it is the people. This might be a distinctive feature of the city-level digital twin in relation to the engineering digital twins. So this leads to our last proposition. City-level digital twin development is an evolutionary process. The usefulness of CDTs lies in driving positive changes through co-development with stakeholders. This is somehow in line with the design thinking paradigm. The diagram on the right-hand side shows the famous double diamond, which illustrating design as a problem-solving process. The key implication is that we need to understand the CDT development as a process rather than an end product. And the most effective way to evaluate the success or usefulness of the CDT is to look at outcome. The next section of the presentation will be sharing some of the lessons that we learned from our local experiment. To introduce the Transport Digital Twin prototype for Cambridge, in a nutshell, it is a data analytical tool for understanding the nuanced car travel demand. What is new about the model? First, we follow a sociotechnical approach for developing the digital twin prototype, which combines stakeholder engagements with technical modeling. Second, we use existing city-scale datasets instead of collecting any new data. And last, learning by doing for exploring a city-level digital twin strategy for Cambridge. We will articulate these points in our next slides. First, a socio-technical approach. We start by thinking about what policy problem that the digital twin trying to solve and for whom. Through extensive engagement with local authority partners, we try to understand their expectations and also the various institutional and financial constraints. We also address the governance issue of CDTs. This relates to the wider impact of the CDTs, the potential risks, and also the future scalability of the digital twin tools. On the technical perspective, we start from developing a problem-driven modeling strategy. This is to say that we don't start from a given modeling method. Instead, we're trying to understand the policy problem, define the problem or define the part of the problem that the model could help. We also think about the level of detail of the model, which relates to the proposition number 2. And lastly, we deal with the difficult trade-off between model comprehensibility and sophistication. If you want to know a bit more about the socio-technical approach in our local experiment in Cambridge, I would direct you to our recent paper on the Journal of Urban Technology. On using existing datasets, the reason why we choose to use existing data instead of collecting any new data is to address the following issues. We observe that there are a large amount of underutilized and even idle data in local authorities and the private sectors. If you look at the data sharing platform of most local authorities, you will find that lots of data set has only been updated a number of years ago. Nonetheless, a very good case here is the London Data Store. If you look at the screenshot on the right-hand side, you see that they actually update this data set by the hour. And this velocity of data generation shows the great potential of city-level digital twins. And second, evidence-based policymaking versus policy-based evidence-making. This is quite a cliche, really. But the implication for us is that by using existing data, we are free from the original intention of the data collection scheme, and now can explore the new use and the new value of the data. And third point is that we believe there is an imperative to demonstrate that the city-level digital twins can generate policy insight with whatever data availability. It's not fair to tell local authorities that you would have to install 1,000 more sensors such that you can build an operational city-level digital twin. However, this doesn't mean that we don't need any more data, but instead, we argue that the city-level digital twin should actively inform new data requirements rather than simply being a data machine. The last point, learning by doing. Cambridge is very ambitious in terms of digital city development. It is one of the first cities in the UK trying to develop a city-level digital twin strategy. However, there are so many unknowns about city-level digital twin, so this raises a difficult challenge for policymakers. So this local experiment actually serves as a co-learning, co-developing process. By following the learning by doing approach, we don't assume that the CDTs will provide ultimate solutions to urban issues. Instead, we are very wary about the claim that the CDTs could solve those wicked urban issues, as claimed by the technology providers. And second, we do want to understand the possibilities, but also the limitations of city-level digital twins in terms of what problems that the city-level digital twins can really solve. Because we know that some problems simply do not lend themselves to a digital solution. And third, how many digital twins we need for one city? We believe that we need a federation of city-level digital twins for various reasons. For example, the varying temporal scale of urban change processes that we discussed earlier. And next point, this is actually our hypothesis. For developing a healthy city-level digital twin ecosystem, we believe that creating monopolies will not help. In fact, we need some competition of models, such that the fidelity and the cost effectiveness of the models could continue to improve. And lastly, we are aware of the wider impacts of city-level. These are really about the unknown unknowns and how, as policymakers, could take proactive measures to contain the risks of these disruptive changes. So far, I haven't talked about what it really does. For modelers, if I may just summarize the nature of the model, it is a rule-based algorithm for inferring the trip purpose of car journeys using large-scale traffic sensing data, specifically the automatic number plate recognition data. For those of you who are more interested about the technical design of the model, I'm happy to divert you to our recent paper on transport policy. Just an update in terms of the recent progress. We are in conversation with the local planning authority in Cambridge, exploring to use the CDT tool as an alternative way to conduct traffic impact assessment. The conventional traffic impact assessment require very simple data inputs, for example, the traffic counts on adjacent roads of the development site. However, those traffic counts do not really reflect the actual and nuanced travel demand. With the CDT that we developed for Cambridge, we can actually conduct a very detailed analysis of car travel demand by purpose, by time, and by location. And through the CDT, we can also enable a very useful prediction and validation loop by continuously taking data from traffic impact assessment, so that we can actually monitor the change of traffic in relation to land development. Confusion of means and ends. This is a comment from Albert Einstein in the wake of discovery of atom bomb. Well, the city-level digital twin perhaps is not as revolutionary as the atom bomb, but we need to understand that the city-level digital twins are essentially the means to achieve better policy outcomes. In fact, Professor Michael Batty, a pioneer in urban modeling, cogently pointed out in 2018 that the time of CDT as a novel concept will pass. This is, of course, a provocative argument, but this actually reflects the wide criticism that CDT as a hype. However, as an academic, I would argue that the aspiration of using digital twin and models to advance the science of cities will last. That's the end of my presentation. Thank you very much.